Hello and welcome to this video on generalized linear models in R. In one of our earlier videos, we had seen correlation regression and how we develop linear models in R. This video we will concentrate upon GLM, that is generalized linear models. These models help us make models, or GLM helps us make models for data which is not normal. If you remember, when we were looking at correlation regression, we had assumed that the data was normally distributed. But here, if the data is not normally distributed, then GLM helps us prepare models for the same. There are three important aspects for GLM. One, distribution of the response variable. Two, linear predictor. And three, link function. We assume that the theory part of GLM is clear to you, and thus we'll take forward the concept of GLM and try to implement those things in R. The formula for GLM is very similar to the one that we did with the LM function, which is for the linear model function. So we have a function named GLM, in which we first argument is where we pass the formula for the model. So y is equal to a plus beta x1 plus beta x2 plus theta x3, whatever number of variables you want to have in the dependence. So first is the formula. Second, you have to mention the family to which the distribution belongs, and give the link function. Clear? And lastly, the data from where R will source the values. Clear? So first the formula, then the family, and then the data, and within the family you have to mention the link function. Clear? We will come to different kinds of families of distributions and the link functions corresponding to each of them. So for example, the null model is where y tilde, if you remember, is used to explain the model. So y equal to is what we write when we write on pen and paper. In R we use the tilde sign. Y equal to 1 or y tilde 1 is the null model. If we have just one variable, but then y tilde x1, whichever variable name is there. X1 plus x2 is where multiple variables kick in. If you want to have, say, x1 plus x square or just y equal to x square, then we use the I function, I bracket x1 square. That's for squaring the variable, or even if you want to do cubing or any sort of power. Lastly, if you want to have multiple variables but interaction of variable with one another also. So for example, if I want to predict the price, if I want to predict the price of a particular commodity based on demand, income, and another variable which is an interaction of both income and demand, then I'll take x1 plus x2 plus x1 colon x2. Clear? So these are the ways in which we define the model or the formula in the GLM function, exactly the same way as we did in the LM function in R. So let us look at a data set now. We name the variable GLM data, and we import a data set which has four variables: income, CIBIL score, wealth, and number of defaults. Income, CIBIL score, wealth, and number of defaults. So we want to prepare a model of number of defaults based upon wealth, CIBIL score, and income of a person. Clear? So we want to prepare a model of number of defaults. So my y, that is a dependent variable, is number of defaults, and the independent variable is income plus CIBIL score plus wealth. So see, y plus x1 plus x2 plus x3. Clear? This is my formula. Family that I have chosen is Poisson, since the number of defaults will be a non-negative integer. So I've taken Poisson as the family, and as you know, link would be the log. Link function is log. Clear? Data is GLM data. Clear? So this is my formula. The model that I've named is model 1. The moment I execute this and look at the summary of the model, I can see that it gives me the formula for first, that number of defaults, which is the y variable, is nothing but x1 income, x2 CIBIL score plus x3 wealth. Family is Poisson, link is log. Clear? This is the whole function that has been designed. You have been given the residuals, deviance, the minimum, first quarter, median, third quarter, maximum. We can definitely do an analysis of residuals to see whether they are random in nature or we can see some sort of trend in that. We will definitely come to that part towards the end of this class. Next up, we have a table of coefficients, their estimates, standard errors, z values, p values, very similar to what we got in the LM model. And here we can see that Sybil score is highly significant. Sybil score is highly significant given our data set, clear, in order to predict the number of defaults a particular person will undertake. Income is absolutely not significant, and wealth is slightly significant but not as much as the Sybil score. Clear? When you look at the null deviance, it is 78.974. Null deviance is the null model, the deviance with the null model, and residual deviance is the deviance with the current model. Obviously, we have income, Sybil score, and wealth as 3 variables, so we have lost 3 degrees of freedom as well. Clear? When we look at the ANOVA of the model can also be seen. Clear? We can clearly see here that how the deviance residual deviance has reduced. What is the difference between each residual deviance, given that we have added 1 variable to the model. So when it was a null model, we had 29 degrees of freedom and residual deviance was 78.974. When we added income to the model, we lost 1 degree of freedom. The deviance reduced by 0.0605, thus the degrees of freedom came down to 28, but the residual deviance did not come down enough, which means that income isn't good enough to predict the number of defaults of a particular person in our data set. Thus, income is an insignificant variable, which was also clear from the table earlier. Sybil score, when they added to the model of null and income, then you did reduce the degrees of freedom by 1, but deviance reduces by a huge margin of 26.7251. Therefore, it shows that Sybil score is highly significant. Clear? We can also find out the residuals by writing model 1 and drop down exactly the same way as we got in the LM model. So see, it gives you fitted values, residuals, offset, terms, formula, boundaries, clear? Various things that you can get from the drop down over here. What if we want to drop the intercept? So we want the model to be, instead of y plus a plus bx1, bx2, bx3, we want it to be y is equal to bx1 plus bx2 plus bx3. So if you want to drop the variable, then the formula remains as it is, that was there, just put a -1. You can see there's a -1 there. The moment you do -1, it will just drop the intercept. So I run model 2, and when we look at the summary of model 2, see the coefficients are there where there is income, Sybil score and wealth, but your intercept is missing. Even the degrees of freedom is 27, which was 26 earlier. Clear? Now, we already know that when we compare two non-normal models, then the scale deviance, the difference of the scale deviance is what we are interested in. Here, the difference of scale deviance is what we are interested in. So we prepare a model called model 3, in which we are taking Sybil score and wealth as the 2 variables. So we have dropped the income variable, and then we will see that if we compare model 3 to model 1, see, they are non-normal, they are based on Poisson. So if we compare model 3 to model 1, is model 3 better than model 1 or not? Our H0, that is our null hypothesis, will be that they are not different from one another, they are as good as each other, and H1 will be that they are different from one another. Clear? So number of defaults is now being predicted on the basis of Sybil score and wealth only. Rest of the things remain same. Poisson family data is GLM data only. I run this. Now when I see ANOVA of model 1 and model 3, clear? So I want to compare model 1 and model 3. And the fact that they are non-normal models, I'll have to conduct a chi-square test. Clear? So the moment we execute this command, we get an analysis of deviance table, where we can see model 1 was income plus Sybil score plus wealth. Model 2 was only Sybil score plus wealth. Degrees of freedom was 26 in model 1. It is 27 in model 2. The residual deviance was 47.225 earlier. Now it is 50.167. When you see the p-value here, it is 8.628%, which means that we do not reject the null hypothesis. That is, model 3 is not significantly better than model 1. They are as good as each other. If you look at the summary model also, we can see this we had already seen earlier in model 1, and in model 3 we have only the Sybil score and wealth. Intercept is again here because we have not done -1 over here. Clear? If we have to compare two normal models, then instead of conducting a chi-square test, we would conduct an F test. That's the only difference. The function is still the ANOVA function where you pass both the models, just that the test will be replaced, the chi-square test will be replaced with the F test. Clear? Next up, if you want to update an existing model, So we had model 3 where we had CIBIL score and we had wealth. Now we want to add income to this model. So you already had a model 3, so we use the function called update. We are updating which model? Model 3, and we are doing what? We are just adding a variable income to it. If you wanted to drop something, we would have put a minus sign over here. If you want to add something, we are putting a plus sign over here. So the new model is called model 4, which is an updation of our model 3, where we are adding income variable to the model 3 existing variables. The moment I execute this and I run summary of model 1.4, it gives you intercept, CIBIL score, wealth, income, all of them. It is exactly the same model that we had built earlier in model 1. Clear? Where we had all the 3 variables. So if I execute model 1 or model 4, it is going to give me the same result in the console. Now the main idea of developing these models is to use it to predict in the future that if we are given an income, CIBIL score and wealth of a person, then can we predict that what are the number of defaults that person will have or that person will incur using a particular model. Clear? So we will use the predict function to predict the number of defaults given the data at hand. So we use the function predict, where we first pass the model in the first argument, then we pass the new data that we have, and then we pass type equal to response. Clear? Type equal to response. Even if you don't write type equal to response, it will by default give you type equal to response only. The data that we have is income is this much. Clear? So income is 2 million, CIBIL score is 798, and wealth is 7.5 million. Clear? This is the new data. So the new applicant, maybe the new applicant for a loan or a new person with an account in the company might have come, and this is the data that he or she has. Using this data, we want to predict that whether the person who has come in will have any number of defaults, and if so, then how many. So we use predict function, and we are basing the prediction on model 1 and the new data that we have. Clear? So at the moment we run this, we see that our model is predicting 0.6746994 number of defaults for this person. If you want to see the fitted responses for all the values that we had earlier, then we just have to run fitted model 1. Then these are the number of defaults that this model would have predicted. So say for example, for a person with CIBIL score 560, wealth of this much and income of this much, our model has predicted 5.897720 defaults, and in reality there were 6. Clear? For the second person with 748 CIBIL score, 2.4 million and 7.5 million income and wealth respectively, it had predicted 2.313575 defaults, and we had in reality 4 defaults. Clear? So these are the fitted values in the model depending upon model 1. Alright. As I mentioned earlier, residuals are a key component of any model that you prepare, be it linear model or be it a GLM model, because if there is any sort of trend that is there in your residuals, then that means that the model isn't a great fit and that we can do much better in it. So a residual analysis is definitely something that every person must do thoroughly. So these are the residuals that are there from our model. Residuals can be calculated in terms of Pearson residuals or deviance residuals. So when we calculate the Pearson residuals, we write type equal to Pearson. Even if you don't write type equal to Pearson, by default R will give you type equal to Pearson only. Clear? Pearson residuals are when Pearson residuals are skewed for non-normal data, whereas Pearson and deviance residuals are both identical for normal data. Clear? When we plot any model of GLM1, it gives us these various graphs that help us analyze that whether the fitted values are fine or not, or whether the residuals are normally distributed or not, or if there is any sort of trend that we can see in the residuals. Clear? So these graphs are very, very helpful in visualizing the problem at hand. using the GLM model. Clear? So the moment I run this, you see here it tells us hit return to see next plot. The moment I place my cursor over here and press enter, you see we get the residuals versus fitted plot. Residuals versus fitted plot. So the residuals are on the y-axis, fitted or predicted values are on the x-axis. If it is completely random and if it is not giving us any particular trend, that means that the model is a good fit. Clear? Next up we have the normal QQ plot. Normal QQ plot is, again, it tells us whether the theoretical quantiles that should have been there as per the dotted line are our standard deviation residuals following the same trend or not. Clear? Then we have scale location, and lastly we have residuals versus the leverage plot. These are various plots that we can prepare or we can make in order to gauge whether the model that we have made is correct or not, and is it the best fit or not. Another way to do is to plot the histogram of our residuals. You can clearly see that this is not at all normally distributed. It is not at all normally distributed, which was clear from the first graph also that we had under plot, where we could see that there were significantly negative residuals as compared to positive ones. Fine. As I had mentioned earlier in the video, that we will tell you what are the various families and their respective link functions. For Gaussian, that is your normal distribution family, your link is identity. For family of Poisson, it is log, we had used it earlier. For family of binomial, link is logit, and for family of gamma, it is inverse. Clear? Let us look at another example. The data that we have at hand is this. We have the ID, age, car group, area, no claim discount, gender, and claim number. So we want to predict the claim number, that is the number of claims a particular insurance company will face on its motor insurance policies. Clear? We have the gender of the person who is driving, no claims discount code, area, car group that the car belongs to, the age of the driver, and the ID. Clear? Clear? So we want to build a GLM one to analyze the claim numbers of motor insurance. We will, since again, as in the earlier example, since the claims are positive integers, we will use the Poisson family. So we prepare GLM model using claim number as the y or dependent variable. We have age, area, car group, NCD, and gender. All the variables we have taken over here, and data is data. Clear? If you see, I have used the function factor over here and over here, because if you see here, when we look at the structure of this data, car group and NCD, these should have been factors. These should have been factors or groups, all right? But they are not stored as factors by default. So when I am preparing my model, I want in my model that these variables should be taken as considered as factors, both NCD and car group. The moment I run this model and put a summary, we can see here that we get a huge table in which, see, car groups have been considered as factors. So group level 1, level 5, level 6, level 8, level 9, depending upon whatever number of levels will be there for car group. So these are the estimates, standard errors, Z values, and P values for the various variables. Even in NCD, you will see there are 5 levels, 1, 2, 3, 4, 5. So it has considered every single level in the NCD group to be a different variable. Clear? Clear? Again, if I go down, I'll see that the null deviance is 4569.9, the residual deviance is 4085.6, degrees of freedom has fallen down by 36, and residual deviance has reduced by 484. This means that this model is better than the null model. This model is better than the null model. We can see the chi-square critical value at 36 degrees of freedom. It will definitely be lesser than 484.3. Clear? So this is a comparison that you can make with the current model as when compared to the null model. We can obviously look at the ANOVA model. You can see here that age, the moment it was added, deviance reduced considerably. So was it for the case of factor of car group. Area also reduced it significantly. So did NCD and gender. So all these variables are pretty significant as compared to the when we look at the model. See, all these are pretty significant. All the NCD ones. Most of the factor car groups are. Areas, some of them are not. Clear? and age also is absolutely significant. Next up, we want to add a variable age square. So first and foremost, we need to add the variable age square in the data set, and then only can we include it in the model. So we put it in the data by writing data $age2. That is the new column that we are adding, age2, which is a square of nothing but the age column that was existing in the variable already. So we use GLM model 1, where we are updating the GLM model 1 by adding a new variable called age2. The moment we run the summary of model GLM model 1, you can see that there is another variable added to it. Clear? If you see the residual deviance, again it has fallen down significantly. Clear? Now if I want to compare the earlier model with the current model, what will I do? ANOVA GLM model, the earlier one, the new one, and because they are non-normal, we will use the chi-square test. The moment I run this, you can see that the p-value is very, very low. The p-value is very, very low. Even when you compare the difference of the deviance in both the models, it is significant. It is significant. 24.3 is the difference between both the models, and degrees of freedom has reduced just by 1. So definitely the second model is better than the first model. So adding age square as the variable was definitely a good option. So this is how you conduct GLM models in R. So GLM function is absolutely the same as the linear model function, and then we can use the chi-square or the f-test to help compare between two models, chi-square for non-normal models, f-test for normal models, if you want to compare between two different sorts of models in GLM data. Clear? You have to simply compare the difference in the deviance residuals of both the models and the degrees of freedom that has increased or decreased as a result of a change in the model. Clear? At the same time, please remember that update function is very, very useful when you want to move from one model to the other model. When you're updating one model and moving on to the other model, the simple function helps you treat the models in a easy and a simple manner. Clear? So that is it from our side for GLM and R. Thank you.